Okay, good morning, everybody. We're going to get started. This is Digital Electronics Lab. And today we're going to continue a little bit of our lecture that we didn't get to yesterday, which was the fractional binary numbers. Fractional binary numbers. And then after we do that short little lecture, don't forget that tomorrow you have the homework problems due, and we also have the quiz tomorrow. And then we're going to talk about lab number 2, which is expanding logic gates. So you want to make sure that you have your lab manual day. If you have it, you may want to think about getting that available after we get done with the lecture. Okay? So, and you can also turn to page 12 in the book. It talks about fractional binary numbers. So just like in decimal numbers, we have numbers that have the decimal point, call that a fraction, the same as 1.25 is the same as 1 1/4. And in binary numbers, we have the same ability to do that with our binary numbers, which is our base 2 number system. Everything, if we look at the decimal point, yesterday we talked about, for example, let's say we have a number, a 4-bit digital number, 1010. We talked about this being the ones place, this is the LSB, this would be the 2 place, the 4's place, and the 8 place. So this 0 has a weight of 1, this 1 has a weight of 2, this has a weight of 4, and this 4th position has a weight of 8. Which we say is, another way to write this is 2 to the 0 using exponential notation, 2 to the 1, 2 to the 2, and 2 to the 3. And all this really means is multiply 2 by itself 3 times, multiply 2 by itself 2 times, multiply 2 by itself 1 time. So it's really just a shorthand notation. Now similarly, if we want to start talking about fractional decimal or binary numbers, then the next number to the right of the decimal place is 2 to the minus 1, okay, which we know from math is going to be 1/2. It's going to be 1 over 2. So in math, if you have a negative exponent, then you take that number to the bottom of the fraction, so you can convert it to 1/2. So the minus 1 means you take that that number 2 and you move it to the denominator. And the next position would be 2 to the minus 2, which is the same as 1 over 2 to the 2, which is, of course, 1/4. 1/4. So this position, the first position to the right of the decimal point will have a weight of 1/2. The next position will have a weight of 1/4. And the next position will have the weight of 1/8. So if we wanted to build a number, let's look at this number, for example. This number would represent, if we wanted to convert it to decimal, we would add up all these weights. So the 1 has a weight of 8, this has a weight of 2, so we say 8, 9, 10. So this would be, if we write it in decimal, it would be 10. Please note that this is 10 and this is 1010. And this 10 is not 10. So we don't use the word 1010 over here, we use 1010. So we have 10 point, and then this 1 is a half, which is the same as 0.5. So we would say 10.5, or we could say 10.5. Is that clear to everyone? Okay. So that's the basic concept of how we do fractions or decimal point numbers in binary. Okay. And of course you have the example in the book, example 1.5. I'll let you guys do that. That's a little bit more complicated, but this is the basic structure of how it would work. Now, the thing that you need to know for the quiz, of course you need to know this as well, but we also need to get into the fractional decimal to fractional binary conversion. And so they have a method in the book on how to do that. And it's similar to the method we used yesterday for dividing. We talked about if you want to convert a decimal number to a binary, then you have this divide by 2 method that we talked about. Well, today we're going to do this multiply by 2 method, and that starts on page 13. So page 13, this is the fractional binary to, decimal. This is the method that we're going to use. So the method is you multiply the decimal fraction by 2 and note the integer part. Okay? So in the book, the example is 0.2. You multiply it by 2 and then you note the integer part, 0.4. So what they mean is you note this part of the result. So let's say that we're trying to convert 0.2 into a binary number. So instead of dividing by 2 like we did yesterday, we're going to multiply by 2. That's the main difference. Okay? So multiplied by 2. You got 0.4. So the integer part is equal to 0, of course, this position. Okay, you discard the integer part. That's step 2. Step 1 is you multiply by 2. Second step. So step 1, multiply by 2. Step 2, discard the integer part. Okay. Discard the integer part, multiply the fractional part of the previous step by 2. So what's the fractional part? The fractional part is 0.4. Okay, so we multiply that by 2. Okay, so we get 0.8. What's the integer part of that? It's 0 again. This is the integer. It's the part to the left. The integer part is the part to the left of the decimal point. So that's equal to 0. Now we continue this. What is the fractional part? Is 0.8. Multiply times 2. What are we going to get? We're going to get 1.6. What's the integer part? 1. So you can tell over here what we're doing is we're building our binary number, binary equivalent over here. So repeat the step. This time, you only take the fractional part. So 0.6 times 2. What do you get? 1.2. What's the integer part? 1. So okay, now we take the fractional part again, 0.2 times 2 equals 0.4. So again, the integer part is 0 over here. So fraction repeats, product is the same. Read the integer parts from top to bottom to obtain the fractional binary number. Thus, 0.2 is a base 10 number. All these are base 10 numbers, of course. Is a 0.00110011, and you can keep going forever. So you can keep doing this procedure, and your result gets. It's kind of like when you do a calculation of a number that repeats forever. You have to truncate. You can't just keep writing the number out forever, like pi, for example, 3.1415. It just keeps going forever and ever and ever. So it depends on how accurate you want to make this number. You can keep going and going and going. What you could do is just keep going until you get all the zeros, or you could just say, how much resolution do you want? Well, I want 4 or 5 digits of resolution. So it's not like yesterday, and that's another difference from yesterday. We kept doing it until we had 0, until we got 0 as our result, and then we stopped. Well, today, with this type of a fractional conversion, you have to, either the problem has to specify, I want this many bits of resolution, or you have to make a decision on your own on how much resolution you want. Just like you would in a normal calculator fractional problem. Yeah.
So the first is the most significant bit?
Yeah. So it would be point, point 0, 0, 1, 1, 0, and then it would keep going on forever, I guess, probably. And that is in your book on page 14. And then you got another example which you can work on your own. Example 1.6 does another example, the same thing, follow the same procedure. So tonight you can go home and you can practice, and it lays it out perfectly right there for you guys. So if you have any questions, you can just check that. Okay. So the next section is hexadecimal numbers, and that's going to be your assignment to read. Did I already give you that reading assignment? Okay. Well, go ahead and make sure you read that. Read section 1.4.
What's that DIG?
Digital.
Oh, okay. That was the best.
Digital electronics. Read section 1.4. Yeah. 1.4, and that's going to be hexadecimal numbers. We call it hex for short.
There are some that should be pretty obvious.
Okay, that looks good. Any quick questions on this? Yeah.
How did you know what to start with at the top, like 1, 2? How did you know to start with 1, 2?
Well, the problem statement would be, say, convert the 0.2 decimal to binary. So that's the problem statement. Okay? Convert 0.2 decimal to binary. So you start with that, and then you have to know everything else. You have to know how to multiply by 2, how to note the integer part and put it over here. You carry the fractional part over to here, multiply by 2 again, take the integer part and put it over there, take the fractional part, move it over there. So that's all you're really doing. Just moving this part over here, moving this part over here, you know. Okay. All right, that's good. We'll be done with that. Now today we're going to work on lab number 2, expanding logic gates. Actually, I'm going to, let's go ahead and use a projector for that. Desktop on. I found this cool little utility yesterday called Screen Marker. Screen Marker. This little thing right here, you can. Because see, I want to be able to write in this PDF file, but you have to have a professional version of Adobe in order to write within PDF. But you download this little free program, Screen Marker. It just lets you draw on your screen. It's kind of cool. Okay, so all right. So expanding logic gates, lab number 2. We want to complete. On the completion of this, the objectives are that you're going to be able to configure a NAND or NOR gate to act as an inverter. Okay. And we talked yesterday. The inverter is a NOT gate. It takes the logic, whatever logic level you have, either 0 or 1. Let's say, for example, we have a logic 1. The inverter will change that over to the opposite state, so from 1 to 0. Or if you have a 0, change it to 1. So it just simply inverts the logic level. But sometimes you don't always have an inverter. Sometimes you have a leftover NAND gate or a NOR gate, and so you want to be able to have a quick way of doing an inverter. Expand the AND or NAND or NOR gate from 2-input to 3-input gate. Draw the logic diagram that conforms to standard digital design practice. Obtain the truth tables of each gate to be tested. So these are the parts we're going to use today. Same part that we used yesterday, except we're going to add the 02 and the 32. And I'll show you guys. I'll do a quick little demo back there on what parts you need to grab and all that good stuff. You can also refer to your book on chapter 2. Just look at the pictures if you have any questions on that. So when you use more than one logic gate in a circuit, it's good practice to draw the logic diagram. Okay. So let's say that you wanted this function. Now we have those 2-input AND gates back there, the LS08 packages. So this, again, this tells you, the 08 here tells you what type of a gate it is. Whether it's like for example the 00 is a NAND gate, has a bubble here. Okay, so the 00 package. The 08 is an AND gate. Notice that we have some things going on here. Notice you have this. This is called a reference designator. Okay, U1A. We call that a reference designator. That uniquely identifies that gate. And then we have U1B. Actually, the U1 tells you which package you have. So let's say that, for example, you have an integrated circuit part here. And it has some pins on it. Now, normally these packages, they have they'll have 4 parts on. They'll have 4 AND gates on them. I mean, it depends on the package, but they can have 4, they can have 2, whatever. But a common scenario is that they'll have 4. So each gate inside of here is going to be numbered A, B, C, or D. Okay, so this one would be A, B, C, D. You have to look at the data sheet actually to find out. And so when you draw it on the page, there's several things that you're trying to convey to the person trying to build this schematic. They need to know what pin to connect. So if this is the tab on the part, then remember this is what pin is this? We talked about that yesterday. What pin is that? If this is the tab, then what pin is that? Pin 1. Yeah. Oh. Is DK down there? Oh, it's down there where Lee's used to be, yeah. And is Sharon down there? She would know about it. Okay. I think they were, yeah, I don't know where they were. Could you ask maybe Sharon Ellie or Sharon Ellis or one of those guys and see if they're available? Sharon may be able to help you with that. But there's, I can't remember where they're in. Was it in the email? Okay. If you can have Sharon call Kathy Holland. Kathy Holland would let you know. Kathy Holland. Yeah, this is pin 1. Remember we talked about the tab. If the tab is here, then you go to the left of that tab and you count counterclockwise all the way around the part. So this would be 2, 3. So this 1 here is designating that this gate is actually connected to this pin 1. Or that this gate internal to that package is on pin 1. This 2 here is representing that that's pin 2. Okay, so that when the person is wiring this thing up, see, they're not going to see this nice little AND gate symbol when they're physically looking at the board. They're going to just see a package. And so they have to know how to wire this thing up. So they need to know that you need to wire pin 3 to pin 4. So what they're going to do over here is they're going to say, okay, I need to wire pin 3 to pin 4. So these get connected together. And that's what the diagram here is saying. It says wire pin 3 to pin 4. And also on the board there's going to be a designator physically on the board. It's called silk screen. It's going to be white, printed on the board, so that physically you're going to be able to see the package and you're going to be able to see the reference designator, and this tells you the pin number. So you have everything you need to know for a technician to wire up that part and get the electrical connections proper. Okay? And if he has any questions, of course, you can always consult the data sheet, because normally you'll get a parts list that will say U1. You'll have a parts list like an Excel spreadsheet or whatever. And it'll say U1 is a 74 LS 08. Many times on the board it will not tell you what this part actually is. It won't really say. Actually, you can read on the package itself. Normally on the package, if you have good enough eyes and you turn it right in the light, you just get it just right, you can actually read it. It'll say 74 LS 08. But if it doesn't, then it's many times it's the engineer's job really to create the parts list, and the technician should be able to have the parts list. That should be something that's given to the technician or given to whoever's assembling the board. They should have the parts list. And many times I'll have an assembly drawing that has a picture of, first off they'll have a schematic. Okay, they'll have a schematic that has this thing wired up. And then they'll also have an assembly drawing that shows where all the parts go on the board. And many times on the assembly drawing there will be a parts list. And the reference designators here will match up with the parts list down here, so that you can reference everything. So the documentation should tell you where everything goes. I'm trying to teach you guys how to read the documentation. So let's. Okay. All right. Now this is a little bit better picture of what I was showing you. Is the data sheet will have this drawing, but many times you will not have this drawing on your schematic. You will only have this drawing. Okay? But notice what's happening right here. If you on the schematic, it'll say pin 1, 2, 3. So it's telling you what this looks like, but it's just not having the square box around it. So the only information they're not telling you down here is where the power pin is at and where the ground pin is at. Okay, that's one thing that you typically have to know, or get the data sheet to know what that is. Sometimes they will have a separate place in the schematic that has. Actually, a lot of times what they do is U1A, the A package, which is right here. How do I know that this is the A package, by the way? This says U1A, this is U12, U2A. This one up here says U1B. Where is U1B at? Pins 4 and 5, which means that it has to be this package right there. Does everyone see that? So that one has to be, this one has to be A, according to the schematic, and this one has to be B, according to the schematic. Now the data sheet may not tell you which one's A and B, but your documentation in your schematic will define what A and B is. Really, it's defined by whatever CAD tool you use to draw it. But normally they should go in order. They should go from pin 1, through 4, this way. So it really should go A, B, probably C, and D. That's the more standard way of doing it. But if it's ever in doubt, just make sure you follow whatever's on the schematic. So that's what we're going to be doing today. What you're going to be doing today is given a schematic like this. Okay. Or a schematic. Now this one's easier because this is all contained in what? One package. Whereas this one is contained in two separate packages. Why is that? It has two different type gates. They normally do not, that I know of, combine two different gates in the same package. Normally, when you get a package, you'll have 4 AND gates, and another package you'll have 4 NAND gates. So this tells you right away that you're going to have 2 separate IC chips. And it tells you the pin numbers. Over here at A, B, C, that's just arbitrary decided by the engineer. Okay, these are numbers that they pick. They may pick numbers. They may pick names on these nets, like input, enable, and clock. Okay, so this doesn't really tell you any information. What you're looking for is pin numbers. Where do these pin numbers go? This package U1A pin 3 gets connected to pin 1 of U2A, and you know that you want this part to be 74LS00. You want this part to be a 74LS08, and you can read that right off of the package. So it's your job to wire this up. Let me see if there's any other. Of course, you guys can read this. It's in your lab manual. Oh, this is an important point. Each gate separately numbered, and then each package is different. Now, for some reason, I don't really understand why, but U is typically used for integrated circuit parts as the beginning part of the reference designator. Typically for transistors, it'll be Q. For diodes, it'll be D. And for ICs, it's just U. And I don't really know where that convention came from, but so U1 and U2. Also note that this is really the engineer's job, but you may be a hobbyist. You may go into design. You may become an engineer, or you may be working in engineering environment where you're doing research and development, and you may work so closely with the engineer that they ask you to do this type of work too. So you never do really know. So, and sometimes you can catch engineers' work if they mess something up. But what you need to make sure is that the input of unused gates, for example, we're only using, for this circuit up here, this very first circuit, we're only using 2 gates out of 4. So what happens to the unused gates up here? Yeah, you ground all the inputs and you leave open the output. Now that's because, first off, if you connect the output to ground, that's going to create a short circuit because the output is a low impedance. That means it's like a power supply. Anytime I say the word low impedance, that's a property of a power supply or a battery or a source. And if you connect this to ground, then that low impedance 5 volts is going to be going to ground, and you can use Ohm's law to figure out 5 over very low is going to be equal to a lot of current. And the reason you want to tie the inputs to ground is because those are very high impedance inputs, and typically they're like MOS capacitor, and so they can have voltage induced on them. So the outputs can flip and flop around, and that'll cause noise and things on the board. So you want to ground them, or you could pull them high through a resistor, preferably. But the easiest thing to do is just to ground them. And you can see that the proper connection for this circuit to make it work is 3 goes to 4. And you can see right here that 3 is connected to 4. So I would expect you on the quiz on Friday, hint, to if I give you this and then I give you this with no wires here, I would expect you to be able to wire up, to draw this wire here, to draw this to ground, to label 1 and 2, A and B. Okay? You need to be able to label 1 and 2, A, B, and C. You need to be able to label the inputs on here, because this would be your job as a technician, to do that. So I would expect you for the quiz to be able to do that right there.
VCC on 14, you said?
Yeah, VCC on 14, ground, because it has to have power. If it's not, what's not really shown here is that the power goes to each one of these little gates. Now, one way to show that over here, many CAD programs, what you can do, a lot of the CAD programs for digital, the power connections are not shown. They're considered global variables in the schematic program. But you can optionally add those in for example, EagleCAD. If you guys are taking in EagleCAD, you can do this. You can actually add on, typically it's done on U1A, on the A package. There will be a symbol, a special symbol that will have 14 and what is it, 7? Can't remember. 7. Okay. 14 and 7. So this would be schematically the way to note. Now you wouldn't have to do that on U1B because U1 is the package. The A and the B just tells you which gate inside of the package. So this would be a convenient way to represent where the power supply connection goes.
That goes counterclockwise too, A and B, and then the top 2 would be C and D.
It usually follows the pin numbers. So whatever package has the lowest pin numbers would be A. Whatever package has the next sequence of numbers would be B. That's typically the way. But that's kind of decided by, well, it may be specified in the data sheet. If you look at the data sheet, and you guys can grab those data sheet manuals and see there how they've labeled them. I would grab one of those for your lab. But I think we're about done. You guys can get started. And actually, I'm gonna go over where you can find everything really quick, and then you guys can get started. So let's follow me over here. Let's make sure. Yeah, the rest of it is hopefully self-explanatory, but if you have any questions, you can ask. Okay, so over here, we look at our data sheet. Packages we're going to be using today are the Sencor 08, 00, and 32. It tells you the materials on the brick right there. So we have the 00. That box is gone, so we're going to have to look on the lab and try to find it. They probably used it last night. 02 is right here. Okay. I'm going to actually leave them up here so that you guys can get in the habit of grabbing them. And 32 is right here. Okay. All right. If you guys need those switches from yesterday, they're on here. And this is, here we go. So in this bin over here, we have all different types of switches. And the one in the middle, the second one down, we have these little chips that looks like integrated circuit chips with drives and little switches. So if you want to test out your AVs, we have other switches. And then, of course, the breadboards are over here. Everyone knows where the breadboards are over here. And then LEDs. You guys want to see the output of your circuit by on and off. You have LEDs over here, down here. So this has all different types of LEDs. I would just grab a red one. And some of these may be infrared. Some of these ones on the bottom. I think these are infrared, so you're not going to see what just grab one of these red ones. And then the resistors are over here. Any questions? Do you have any questions on the lab? So I would suggest that as many people as can work on their own, because I noticed yesterday that some comments were that I don't think they were done on their own, they relied on the partner watch. If you work by yourself, you may learn more. But you can work with someone that, it's important that you learn these skills. And we have 24 beaches, so go ahead and try to work by yourself today. Yeah, we got it. Can anybody find the 0 to 0 code? Hopefully that is walk off. Did anybody find the 0 to 0 code? Oh, here's You don't need that other box. You can just use the power supply. I haven't found them yet. You can't find the 0, 0, then you can use a different one. If you can't find the 0, 0, just use 2 NAND gates. Okay. Can't find the logic gates. Just use the use an 08. You got to use an 08 to 00. You can add it. You can add it there. Yeah. Yeah, you guys have to have a resistor for the LED, just like yesterday. You can do 330 or 500 or 1K, something. Just currently with a resistor. They'll just make it dimmer. You can try it out if it works. I mean, in practice, you want to use the smallest one you can to, you don't want to use it. Yeah, guys, I just noticed the parts that I noticed while the parts were wrong. The schematic is right, so the first is schematic is the part. Yeah, the parts list is wrong. That 32 should be 08. It does exist in there at the end on the parts list, so I think that should be 32 should be 08.
Right.
What is 32? I don't know what 32 is. What 32? Is 4 gig. We don't even use 4 gig basically. Yeah, we're not using it. You guys see 4 gig? Yeah, there's like no order there.
Oh, it's in there.
There's 4 gig?
Number 5. 0.
Oh, number 5 is 4 gig. Yeah.
They just think.
Oh, this is the logic diagram. You're not actually using the chip, right?
That's the second.
Yeah, we're not gonna be doing anything with it wired up.
Oh, yeah.
I'm going to go around and take row while you guys are doing this. Don, yeah. Yeah. Thanks, Don.
Yes, sir.
So you go by Don instead of Donald?
Yes.
Okay. Got that right here.
Jason Planning.
What do you do again, Jason?
For what?
Where do you work? Do you work somewhere? Or?
No, not yet. I just
Where do you live at?
Mooresville.
Mooresville?
Yeah. Know anybody there?
No, not yet. Not right now. But I do know some people going to hire. Asthma.
Who's that?
They make motors.
Yeah.
Automotive applications.
But they make for the big three, yeah, electric motors.
Yeah.
It's all automated, like
Yeah.
robotics.
Gotcha.
And they're ramping up. They're adding new facilities. Yeah, so 100 employees.
Really? Cool.
Now, where do you? Give me something about company members. Where do you? What did you do? What did you used to work? What is it, like manufacturing?
Yeah, it's
Did you ever take Eric's classes at electrical wiring?
this is just a job I got.
Oh, okay. Okay, that's good. Thank you. Let me see if I can... Business manager. Oh, you're the one that likes to tinker with electronics. What have you done? Okay. Is it microprocessor?
Yeah.
Okay, so you built it. The lithium-ion power plant? That's cool. Yeah. Okay. Okay. You must have some time at home to do because it takes a lot of time. Okay.
I work live.
Yeah. That's cool. You ever did any work on Elance? Sorry, Elance. If you go on Elance, there's jobs that they post on there. Electronics job. Well, it has all types of jobs, but I did a job on it. But you'll find all kinds of cool projects on there. You know, some guy wants to, stream video or music from his guitar through Bluetooth, and sometimes they want to pay you $100, sometimes they want to pay you $1,000, $2,000. So yeah, you can make money off of this. Sounds like something you should do because go to Elance. It's free to sign up. Elance. It's kind of like freelance. Oh, gosh, like freelance. Yeah, and it's free to sign up. And I made a few $1,000 on that one summer. Yeah.
This seemed like a nice step.
I think it would be a good candidate for the rocket program. We're going to we usually use Arduinos on that, so. Yeah, I know. It's good when you're right now. Yeah, if you're
I am
interested.
not knowledgeable, so that's why I'm here trying to get
Okay.
all the little missing things right here.
Draw the one over the end. Yeah. 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 Yeah, so draw the mark there. Well, no, this is different. Draw the mark there of an inverter. Well, to use this as an inverter, you have to look at the truth table for. Oh, here you go. Here's the truth table. Oh, there it is, right there. So if you think about this inverter, they want you to. Oh, I don't think this is AND gate. You have to have both inputs here. And AND gate is the opposite of that. So AND gate, we'll put AND gate over here. So that would be 1, 0, and AND gate would be in this inverter. So the inverter is just simply 1 and 0. So how can you use this gate to get that function? So you want 1 when you have a 0. Anytime you have a 0, you have a 1. Yeah. What if we connected A and B together? Connected A and B together. That way you wouldn't have this case. You only have if you connected those physically together. So if you go over here, connect 1 and 2 together, then you can only be a 0, 0, or a 1, 1. See? And that would make it an inverter. Yeah. I guess we didn't really. Okay. Yeah. black part is trying to show you that all these are different. This red one is showing you all the these are different. There's a separation. Now this is a separation too, because that's the reason. In fact, you can see these are just different screws. So there's no connection across these there's no connection here. That's no, you can put there, you know, it's my favorite spot. Really what I want, I'm going to just make sure that yeah, I guess today, guys, what we're going to, since we don't really have time to finish this entire lab, I want you to focus on number 5. So if everyone could just skip ahead to 5, because we're not going to have enough time to complete the lab.
I haven't got any voltage on my bus.
You have to connect. You're going
I
to
got
have
it
to.
here, but I don't have it on the actual.
Well, this is not actually connected here. You have to
Oh,
actually
you have
put a
to
wire.
connect it? Oh,
Yeah.
okay, I didn't know that.
If you can, everyone please just turn to number 5 and focus on that one for me.
Okay.
And you guys can work on the rest of them at home.
Ecologic
Some of that
diagram.
1, 2, and 3 is just things you can do. Number 5.
Ecologic diagram.
Yeah, he gave me action on these. No, he did all these. He already fixed these. He didn't do more. Yeah. Yeah. I think he has to do right. Yeah, that one's right. He fixed these for me. They had to do a network. Yeah.
schematic.
Let's see. Go to computer.
What's the schematic for an OR gate? What's it look like? That's an OR gate? Okay.
I mean, I need. Yeah. Well, he said he made the workforce technology 211. He made that. Log in. So that's what he did. He gave admin rights to that. But I think he said he had to push it in the network to work. He wanted to see network. I don't know if it's something that Scott will have. Oh, okay. Guys, how are you guys doing with number 5? Yeah, there you go. How are you doing with number 5? Where's your lab book at? Whose book is this right here? Okay, let me show you how to do this really quick. This is going to have to go. Make a logic diagram including pin numbers, part numbers, and designators that makes a 3-input OR function. In fact, can everyone come over here really quick? Since we're running out of time. I'm going to show you the solution to number 5. Show you the solution to number 5. Do you mind if I draw on here? Sorry. Okay. So it says number 5, make a logic diagram including pin numbers, part numbers, and chip designators. U1A. That creates a 3-input OR function. Okay, the thing is that we only have, actually it doesn't really show. Where does it show? Over here. This shows all your gates that you have over here on page lab 1. This is the OR gate 32 package. So in order to have a 3-input OR, we only have 2 inputs on these, so we want 3 inputs. That's what the problem says. It says 3-input OR out of a 2-input OR. That's the key statement right there. We only have 2 inputs, we want 3. So how do you do it? This is how you do it. You connect this one to that one, like that, okay? So the output of one goes to the input of the other one. Now, how do we put the designators? It says designators, including pin numbers and part numbers. Okay, so that's all the key information. This is the logic diagram. So we did the logic diagram. That's step 1. Pin numbers. Okay, what we have to do is we say, okay, this is pin 1 and that's pin 2. And it doesn't matter which one you grab. If you grab pin 1 and 2 and 3, we call that pin 3. See what I did right there? I'm making sure that the technician knows, because see, the technician is not going to have the data sheet. He's probably not going to want to look at the data sheet, right? So whoever's doing the design, the engineer, is going to put all the information that the technician needs in order to build the circuit. Okay, so they didn't have to go, because typically you're going to have a drawing with all kinds of packages. You don't want the technician to have to go look up 20 different drawings. So this tells the technician pin 1, 2, 3. Now we're going to call this. We'll just call this U1. We'll call it A. That's the designator part. So that's the check mark is done. We'll call this one U1B. Okay, if we use that one as U1B, then if we go in sequence of the numbers, then this one would be B. So we're going to label this one B. And then since I used this part of the gate, okay, that's pin 4. Does everybody see that? That's pin 4. I'm going to put a 4 there. Now, what pin is this one right here? Anybody tell me what pin that is? Pin 5. Does everybody see that? That's pin 5. Now the output of this goes to 6. Okay, so this is going to be labeled 6. Now it says, also it says on here, what does it say? Part number. It says I want the part number on there. So now it wants me to put the part number. So we're going to put, what is this? 74LS32. 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 Now we have what? Pin numbers. We have a reference designator. We have the part number. And we have the schematic. Now we have all that we need. Now if you wanted to, you could call this A, B, and C. You could call this Y or whatever. As far as, but it doesn't really ask you to do that. But that's what you need to know how to do for the quiz on Friday. And to be able to do it for any of these packages, like if I give you an AND gate and ask you, I'll give you the logic diagram. I think I'm going to give you the logic diagram. I'm going to ask you to build the circuit and to wire it up. Like if I gave you this, would you be able to wire that up? Here. You know, could you? Well, you know, all you have to do is connect 3 to 4. Connect the wire from 3 to 4. Connect this pin to VCC, this side to ground, and then label these A, B, C, and Y. Just like here. That's basically what we're trying to teach today. Pin 3, you're going to take a wire like that. You put a wire from 3 to 4. See there? 3 is going to 4. Yeah, I could. Okay, is that good? Kind of. Yeah, that's an AND gate. Yeah.
I need to draw it.
Yeah, you can't.
I need to study that.
Well, when these very first labs were, the labs don't really match the book, so the very first lab is just like you're kind of behind a little bit in the lab, and as we do more, you'll catch up. So it's kind of hard in the beginning because you need to really learn the basic theory of what 1 and 0 is, but you also need to really do hands-on practical things, which it's kind of hard in the beginning to do that.
What is this doing? Like making 3 inputs?
It's 2. Yeah. In case you had 3 inputs, and maybe you had a switch on the wall, maybe you had a stop button, and maybe you had another toggle in order to do certain functions. Or one input may be a sensor, like a proximity sensor, from a piece of machine. You know, or maybe a button, the other may be a stop button. So, yeah, it has lots of different.
It'd be nice to have more time.
Yeah, I know. Yeah.
Well, I've wired up my program and stuff like that.
We have to work with on the quiz.
I'll give you everything you need to know on the quiz, and you'll just have to be able to assimilate the information together.
And the other two, as far as knowledge.
Mainly what I'm looking for is you to be able to wire and to read those pin numbers and schematic diagram, and be able to wire up the actual package, just like you would if you were a technician and set down an actual breadboard. Oh, okay. Yeah. I realized when I was talking to you that there's no way you're going to get to this if we're like over here with this because I was like, I should have told you guys at the beginning. I mean, this would take a long time. This would take probably a couple of hours. And by the time you get all your parts together and you like sit down and have the parts thing, it takes a long time.
I was already pushing it. But when I had the sheet thing and jump, you released it.
Make sure before you guys leave that I have everyone here. Actually, I'm just going to call the row really quick because I didn't get around to everybody yet. John Witherspoon. John Witherspoon. James Campbell. Leon Elkins. Christopher Drew. Dakota. Where's Dakota at? He's not here today? Santuan. There's Santuan. Clarence.
I'm here.
Oh, there you are.
All right.
Benjamin Bettinger. Benjamin. Kevin. And Tyler. Yeah. Oh, sorry. Did I do that again? Oh, okay. Yeah. As long as I don't do it on mine, it'll be fine. One thing you can do with this one is just get rid of everything over here. You can calculate that stuff. You know what that's. So you can kind of you can walk around.
My name's Don.
Don, okay. My name's Fred. My bad name
I would
is
do this
Don.
separate. I would do this separate.
Okay.
I would do this. I'd calculate that one. And I would calculate across here. Like this one, I would use the divide by method. Like 87. Remember the divide by method? Divide by 2? Use the divide by method. This part. Yeah. And for this part, use the multiply by 2. So I would do the 7. Now this number here would be 1 point. So you could just say
Oh, yeah.
0.75.
Yeah, but it's not working. I got too much voltage drop.
So energy part.
The light's still not coming on.
It's no resistor.
That'd be 1. So then 0 times 2. So really, that'd be the energy.